This video will cover section 4 of chapter 3. In this section, we'll be looking at experiments. We'll look at definitions of some terms involved with experiments, the necessity and the importance of randomization, the idea of a control in an experiment, blindness in an experiment, the pitfalls of running experiments, and some specific designs of experiments. Remember, there are 4 processes in statistics. In this section, we'll be looking at experiments, which is part of data production. Remember, there are 2 types of study designs: observational studies and experiments. Remember that an observational study is a study in which the researchers have no control over the values of the variables. They simply record what's already happening. The drawback to observational studies is the presence of confounding variables. Look at this example. Men who drink beer are more prone to lung cancer than those who drink red wine. Can you think of a confounding variable here? I think the most likely confounding variable is cigarette smoke. People are more likely to drink beer in a smoky, crowded bar than they are to drink red wine. The second type of study design is an experiment, where the researchers have control over the values of the explanatory variable. If an experiment is well designed, it can provide convincing evidence of a causal relationship between variables. Let's define some terms used in experiments. A factor is an explanatory variable in an experiment. The treatment is the value of that explanatory variable that the researchers choose for the individuals in the experiment. A control group is a set of individuals that do not receive treatment or get the most basic treatment. These groups are often included in experimental designs to provide a basis of comparison. If the individuals being studied are humans, we more frequently use the term subjects. Let's look at an example. Here, researchers are testing if sugar causes hyperactivity. The first step in running this experiment is selecting a sample. Once the sample is selected, the researchers will randomly assign some of the children to low sugar consumption and some to high sugar consumption. The randomness of this assignment is critically important. Why? Because the randomness helps mitigate potential confounding variables. The reason why is if there is some confounding variable, let's say caffeine intake, then as long as the assignment is done randomly, children with a high caffeine intake should be approximately evenly distributed between the high sugar and low sugar groups. That means the effect of caffeine will be spread out between the 2 groups and won't be concentrated in one or the other. Let's make sure that we understand the difference between an experiment and an observational study. In an experiment, once the sample is taken, the researchers decide which subject gets low sugar intake and which subject gets high sugar intake. At the point at which the sample is selected, the sugar intake has not yet been determined. What makes this an experiment is that the researchers assign the sugar intake. In an observational study, the individuals have already had the values of their variables selected themselves. The researchers have nothing to do with the values of that variable. That's what makes this an observational study. In this sugar and hyperactivity experiment, there are a couple of issues in our selection process. What individuals will be included in the study? And of those individuals, who consumes low sugar and who consumes high sugar? The question this raises is, at which stage is randomization important? At the first stage, the selection of the sample, we need to worry if we get volunteers. If we have volunteers, non-compliance may be an issue. In other words, if people sign up for this experiment and they get placed in the opposite group than the one they wanted to be placed in, they may not follow the rules to make sure that the experimenter has chosen the right value for them. In other words, if they really like sugar and they get placed in the low sugar group, they might break the rules for the low sugar group and eat too much. In the second stage, the assignment has to be random. It has to be random. Volunteering at this stage is not okay. Why? As soon as the individual being studied gets to choose the value of their variable, which is what happens when they volunteer for the treatment they get, this becomes an observational study, and we have to worry about confounding. Let me say a few words about control groups. Remember, an experiment is a study in which researchers manipulate the value of the explanatory variable and then observe the value of the response variable. This says nothing about control groups. So, by our definition, control groups are not necessary. Sometimes they can't be used at all. For example, if every subject must be treated, this may be an ethical concern. If we think that some sort of new treatment that encourages blood clotting in trauma victims, we want to see how effective it is. Well, the control group would get nothing, but remember, they're trauma victims. Their lives may be in danger. They must get some sort of treatment. We may have no control group if the simulated treatment is risky. Let's say there's a new treatment for a heart valve defect that involves open heart surgery. In order to have a control group, we have to give the control group something that seems like they have received the treatment. But performing open heart surgery on someone and doing nothing is not a good idea. If the experiment, for whatever reason, is poorly designed, there may be no control group. If control groups are possible, ethically and realistically, then we probably ought to have them. But remember that as long as the researchers control the values of the explanatory variable, we're looking at an experiment. Now, we've used the word control in several different ways. Let's take a moment to look at the ways that we've used that word to make sure we understand which definition we're talking about in context. In an observational study, we might control for a confounding variable by looking at two samples. In an experiment, the researchers control the values of the explanatory variable. Hopefully that happens at random. And in experiments, there is often a control group, which is a group of individuals that get no treatment. Remember that observational studies may never be used to identify causal relationships. Experiments, though, often can give very, very good evidence for a causal relationship between variables. That is to say that the value of one variable causes a value in the response variable. But we must be careful. There are two problems we might run into when it comes to concluding that there is a causal relationship between variables. The first is if the subjects are aware of which group they're in, the treatment group or the control group. The second problem is if the researchers know which individuals are in the treatment group and which are in the control group. We'll explore these two problems in more depth in the next few minutes. The placebo effect is the noted effect that subjects who are in the control group respond to their fake treatment. That fake treatment is called a placebo, and the placebo effect is the effect of an improvement in their whatever it is based just on the idea of treatment. An example of this is if researchers are testing a new drug to treat headache, let's say. They divide the individuals into two groups. One group gets the actual new treatment, the new medicine. The other group gets a pill with nothing in it, no drugs at all. There's a good chance that overall the individuals in the control group will report improvement in their headaches. This is due to the placebo effect. A blind subject is a subject that doesn't know whether he or she is in the treatment group or in the control group. On the other hand, if the experimenter knows into which group a particular subject falls, we have to worry about the experimenter effect. This is when the experimenter introduces bias when he or she records the values of the variables. If they're testing a new drug, for example, and for, let's say, again, for headache, which is not something that can be measured with a machine necessarily, in order to determine whether this new drug works, the researcher will have to maybe ask a series of questions to each subject. The subjectivity of that opens the door for the researcher to report maybe better results for those in the treatment group than for the control group. A blind experimenter is an experimenter or researcher who doesn't know which group a subject is in when collecting data. Let's look at an example. Let's say we are a researcher looking at the relationship between sugar intake and hyperactivity. Suppose that after the children are randomly assigned to one of the two groups, low sugar and high sugar, researchers find that the proportion of children in the hyperactive group is greater for those who consumed higher amounts of sugar. Can we conclude that there is a causal relationship here? Probably not. There's a good chance those kids know whether they're in the low sugar group or the high sugar group, and that might change the way they behave. How could we make this better? Well, if we can, make sure that the children don't recognize which group they're in. This may not be possible. On the other hand, let's say that we have children randomly assigned to diets where the diets are sweetened either artificially or with sugar. So presumably this keeps the kids from knowing which group they're in. And the researchers find, sure enough, the proportion of children with hyperactive behavior is greater in the group that had a higher consumption of sugar. Now can we conclude that sugar causes hyperactivity? Well, again, there's a problem with this. If the researcher knows which group each child is in, it could change the way they assess their behavior. So if they're watching a group of kids play and they know which ones had high sugar and which ones had low sugar, they might be watching the high sugar kids more carefully for signs of hyperactivity. This is even more of a problem if this is a subjective assessment, which in this case it probably is. How do we make this better? Make sure that the researchers are blind, that they don't know which group each child is in. In general, if we conclude that there is a causal relationship between two variables, the best evidence comes from an experiment that is randomized, controlled, and double-blind. Randomized means that the selection of the sample was random. The placement into each group was random. That there is a control group, and that it's double-blind. Both the subjects and the experimenters do not know into which group each subject has been placed. We've been spending a lot of time with this notion of the relationship between sugar intake and hyperactivity. Back in the 1970s is when these studies saying that there is a relationship first came out. But there's a good chance that those experiments were single blind and not double blind. Since then, those results have not been able to be replicated, which means that there may have been some bias introduced by the fact that it was single blind. There are some other troubles that we can run into when we are running an experiment. First is a lack of realism. If the situation that we place the participants in is not realistic, it may be hard to draw valid conclusions. Next, the Hawthorne effect, which is the effect of subjects changing the way they behave because they know that someone is watching them. Non-compliance is a problem. If we are testing a new drug, for example, that requires the subjects to take one pill every 4 hours for 4 weeks, after a while, some of those participants are probably going to quit taking it, or quit taking it with the regularity at which it had been prescribed. It could also be that the treatments that the experimenters wish to give are unethical, or impractical, and even impossible. Let's look more closely at the lack of realism and the Hawthorne effect problem. Suppose researchers are looking for a relationship between watching television and eating. In this case, the study participants are placed in a waiting room, knowing that they have an interview coming. Half of them are put in a waiting room with a TV on and snacks available. The other half in a room with no TV, but also has snacks available. The experimenters look to see how much of the food is consumed in each room. If the participants in the room with the television snack more, can we conclude that, in general, people snack more when they watch television? Probably not. In this situation, there's a lack of realism. This setup is not exactly the way that people usually watch television. At home or with friends, on the couch, in a relaxed setting. not waiting to be interviewed for some sort of study. There could also be bias brought about by the Hawthorne effect. If the people notice that there's a one-way mirror in the room, for example, they might correctly assume that someone's watching them and not eat as much. Let's look at noncompliance. Let's say we've got a study looking at relationship between sugar and hyperactivity. The researchers randomly assign 50 children to the low sugar group, 50 to the high sugar group. But over the course of the study, suppose that 20 in each group drop out. Of the 30 that are left in each group, what if we notice that the level of activity is much greater in those in a high sugar intake group? Can we conclude that sugar causes hyperactivity? Here we need to worry about all the people who dropped out, those who were non-compliant. The 30 people that are left over in each group might be substantially different in some way for some possible confounding variable that makes that new sample of 30 substantially different from the original sample of 50. In other words, these samples are no longer random. Here's another example. To test if stuttering is a learned trait rather than an inborn trait, a researcher in Iowa randomly assigned subjects to two groups. The first group, the control group, were 11 orphans in a speech therapy class. The treatment group was 11 orphans who were badgered and interrupted in their sessions with the speech therapist. Of the 11 in the treatment group, 8 developed a stutter. What's wrong with this? This is pretty clearly an unethical experiment. It's worth noting that in 2007, the state of Iowa settled a lawsuit to pay these subjects nearly $1 million. Let's look at impossible or impractical treatments. Taller men get married sooner, get promoted quicker, and earn higher wages. There is a link between obesity and low socioeconomic status in women. Here, these statements are hard to verify using an experiment. The reason for that is, remember, in an experiment, the researcher must be able to control the explanatory variable. Height is something that cannot be controlled by an experimenter. Obesity is something that is very difficult to control. And there's also an ethical question there. If you force someone to become obese because that's the group they were placed in. Socioeconomic status is not something that can be controlled easily. The only way to do it is with a lot of money, by giving it away to change the socioeconomic status of a person. There's some modifications that we can make to a randomized experiment. One of those is blocking. In a blocking situation, we first divide the sample into groups of subjects that are similar in some way. So if we're looking at another sugar hyperactivity experiment, and we think that gender might play a role, we might first divide our sample into boys and girls, and then look at what happens. In that case, we might be able to, in addition to establishing a relationship between the variables, decide that the relationship is stronger, for example, in one group than in the other. We may also do a paired design. in which, remember, we measure the value of our variable for each member of a pair, where one member of the pair is in treatment, the other member of the pair is in control. There again, you might be thinking about siblings or twins or a married couple, or, and this is important, a before and after, looking at what happens to a person before treatment and then after treatment. That way the person is effectively in both the control group and the treatment group. That notion of blocking might sound familiar. Blocking is sort of the same process in an experiment as what we call stratification was when we were looking at sample design. Let's look at an example of blocking. A study tested the theory that use of stronger sunscreen causes people to spend more time in the sun. So, before a vacation, a group of at least 40 students were given a weak sunscreen and at least 40 students given a strong sunscreen. Then students recorded how much time they spent in the sun each day. How can we incorporate blocking in this situation if the researchers think the location of the vacation plays a role in the relationship between type of sunscreen and the amount of time spent in sun? Well, perhaps they can block the sample by vacation region first. Then inside the group of people going, let's say, to the beach, that group gets some put in the weak sunscreen group, some in the strong sunscreen group. Those who are going skiing, that group would be divided into weak and strong sunscreen, and so forth. Let's look at the same situation, but this time with a paired experiment. How can we incorporate a paired design into this sunscreen experiment? Well, the way to do that would be to look at pairs of students going to the same place, maybe sharing a hotel room together, and in each pair randomly assign one to weak and the other to strong sunscreen. That also takes away factors like let's say it was raining all week in one place that some students went, but it was sunny all week in another. That might change things unless one person from each group is in each location. That way, the amount of sunny days would be evenly divided between the two groups, low sunscreen and high sunscreen. This highlights the advantage of a paired design. Making sure that one member of each pair is placed into the treatment group and the control group. Make sure that those two groups are as similar as possible with respect to all other possible confounding variables. This gives us some of the strongest evidence we can get that the treatment is responsible for any effect that we see. Often we see a combination of a paired design and a two-sample design. Many studies that are looking at effectiveness of a new drug will randomly assign one group to be the control group with a placebo, the other group to receive the drug in question. Then responses would be assessed both before and after the course of treatment, and then compared to look for benefits or side effects. What part of this is two-sample and what part of this is paired? The two-sample part is the assignment to two different groups, either placebo or drug. The paired design is the before and after, looking to see what the value of the variable was for each subject before the course of treatment and after. To wrap up, we looked at the definitions of some terms involved with experiments. We talked about the importance of randomization and the two stages of selection. We talked about what a control group is, what a blind study design means in two different ways, both for the participants and the experimenters. The subjects should be blind in order to avoid the placebo effect, whereas the researchers should be blind to avoid the experimenter effect. We talked about some other problems that one could run into with experiments, lack of realism, the Hawthorne effect, non-compliance, and unethical or impractical treatment. Then we looked at some specific experimental designs, like a blocked design and a paired or two-sampled design.